All right, now we are going to continue our pursuit of getting into this paper's analysis of why or how we can interpret the curvature scalar. Remember, our goal is to interpret all of the curvature related tensors. The curvature tensor itself, we've done. The Ricci tensor, alpha, gamma, we've done. We're working on the curvature scalar now, which is hard, and ultimately we're going to want to do the Einstein Tensor, which of course is the critical component of the Einstein Equation. So we're kind of walking through interpretations of these things, and right now we're trying to get to the interpretation of R, and our study of the interpretation of R is going to require an understanding of Riemann normal coordinates, so I'm taking the chance now to study those things. In our last lesson, we discussed tetrads, and we're now going to broker that to a full understanding of Riemann normal coordinates. Now, in this first lecture, I'm going to go through this. I don't want to say we're going to go through it intuitively first. We're actually going to rigorously develop this idea of Riemann normal coordinates, but we're going to go through it the way Meissner, Thorne, and Wheeler goes through it. So if you have Meissner, Thorne, and Wheeler, you can look in that book and you'll see exactly the analysis we're doing here. Meissner, Thorne, and Wheeler also has these pictures that are related to a related concept. Don't confuse these pictures with Riemann normal coordinates. They are very similar, and we'll probably get to them later. But these are something called Fermi normal coordinates, which are different from Riemann normal coordinates, but we don't need to worry about that. I just want to make sure that if you have Meissner, Thorne, and Wheeler, which many of you do, you can follow the analysis there. The next lecture, we will go through a more mathematical proof that sort of binds all of this stuff that we wave our hands at in this lecture into a more mathematically rigorous picture. So this is going to take 2 lectures to get through. Okay, so let's begin. All right, so we begin with Alice's lab, which is going to be right here, set up with the origin of her tetrad right there in space. So let me draw in the tetrad that she picks. And we won't get too particular about this tetrad except to say that it is orthonormal. So once she has this tetrad sitting out there in this lab in space-time, what we can start imagining is she can construct vectors all throughout the tangent space based on her basis system. So she could, for example, create this basis vector, this not basis vector, but that vector. She could create that vector. She could create that vector. Any one of these vectors, this would be x, a, e, a, and y, a, e, a, and z, b, e, b, right? All of these vectors are now expressed in her tetrad basis system. So with that in mind, keep that fact in mind, now let us remind ourselves about the geodesic equation. If g is, if this function is a geodesic curve, and this is the parameter for measuring along the curve, and this is the coordinate component, this, if I give you a parameter value, this is 4 functions that will return the x0, x1, x2, and x3 coordinate of any point along the curve. That's just a little reminder on how this works. So such a curve has to satisfy the geodesic equation. And as a reminder, this is the geodesic equation. So we know that by definition, this curve will satisfy this equation. And embedded in this, of course, is the connection on the manifold, right? So this is some manifold in space-time. It has a connection, and that connection is derived from the metric, g mu nu, right? So with this in mind, we can now say, well, remind ourselves that, well, this is a second-order differential equation. And ergo, it is perfectly and uniquely defined once we know 2 facts. We would know boundary conditions, for example, or initial conditions. And in this case, we will learn the initial conditions, right? The initial condition is that we are going to make sure that the geodesic, whatever this geodesic is it goes through this point. It goes through the center of the lab. And the other initial condition is that its tangent vector at the center of the lab is some defined known vector, which I guess what we'll do is we'll call that vector v, right? So let me erase these other vectors real quick. Okay, and now we will just define just one vector, and I'll draw it, say I'll draw it here. I'll draw it in the x1, x2 plane. So this is a space-like vector, right? This is a space-like vector in the x1, x2 plane, but it does define a geodesic because we know where it's an initial point, or a point that's definitely on this curve, and we know the derivative of the curve, or the tangent vector of the curve at that point. So we know that let me do this. We know this. We know that the tangent vector of this geodesic curve at Alice's lab, the point A, that evaluated A, equals, oops, I wrote 0. It doesn't equal 0. It equals some known vector v. And I'm going to put a little arrow on top of v just so we remember that this is a vector and it's an element of the tangent space of A. And furthermore, it has components, right? We can give the components as v alpha e. I don't want to use Greek letters, right? I don't want to use Greek letters. V a e a. I won't bother with the hats right now. I'll only use the hats if there's numbers. All right, if the numbers E2 hat, E0 hat, E1 hat. If it's not a number, I'll just leave it with a Latin index. So the Latin index will represent the tetrad basis. The other thing I know for the initial condition is I know that, what is it? It would be G mu of 0 equals Alice's point A. Right? So that's enough to fully define, with these two initial conditions in this second order differential equation, this curve is well-defined, and well-defined in math means it exists and is unique. It is unique. So the point is that now, with all of this in her arsenal, she can start basically shooting geodesics out from her laboratory, and that is going to be the foundation of the Riemann normal coordinate system. Okay, so to understand how this works, I will just break it down in 2 dimensions as a small picture. So now let's just have a look at this. We'll just lay it out there flat. And she picks, so she's established her lab, right? Her lab is at this red point, P, or A, I guess we're calling it. And she selects some vector in the tangent space, say this vector right here. That's V. And then she solves the geodesic equation and uses as her initial conditions V and the point. And from that, she ends up deriving a geodesic. And that geodesic comes out something like this. And let's just draw it there in blue. So now she could do this in principle for every single vector in the tangent space, every single different vector in the tangent space. So when she picks, say, another vector, I'll do that one here, right? And that vector will have its geodesic, look something like this. And then maybe E1. E1 is itself a vector, right? The basis vectors are count as vectors, so they define some geodesic. And the actual shape of this geodesic is highly dependent on, of course, the connection. No connection, all these geodesics are completely straight lines. So, but she can do this with impunity, right? Well, impunity, that's not the right way of saying it. She can do this without restriction, right? She can just pick vector after vector after little vectors and big vectors, and any single vector that she can devise inside the tangent space, she will create a unique geodesic. Now, what's important to understand is that every point in the nearby space-time, right, in the nearby space-time, any point will be on one of these geodesics. There is a caveat to this one geodesic thing, which I got to be careful about, but I'll get to that in a moment. Oops, I'm drawing points on vectors. That's not right. Hold on, let me get rid of those last points. On the geodesics. So every point in space-time should be on one and only one geodesic. And because of this, what we're going to do, the general plan is, this point here is on the geodesic defined by this particular vector. So to that point, let us say, okay, we're going to associate that point with the vector that produces the geodesic on which that point lies, and then it's also a certain distance s along the geodesic. So we need to know how far along. So this tells us which geodesic it's on, and this tells us how far along the geodesic it is. So in order to identify this point using such a system, notice I need 5 numbers, right? 4 numbers to describe the vector, because it's a 4-dimensional vector space, and 1 to describe the length. And this seems a little bit overdetermined, right? Because we know that points in space should only really require 4. But maybe this system is just inefficient, right? Maybe it's just an inefficient way of labeling points or something. But nevertheless, understand that it can be done. I specify a vector, and it will determine a geodesic, and then I specify a path length along the geodesic, and I can identify every point in the space-time that way. Now, let's get to the caveat. So the caveat involves vectors that are pointing in the same direction. So imagine this vector here, which I guess we'll have to call V, and we'll call this V. And then imagine another vector that's going in the exact same direction, but is longer, right? Here, I just redrew it. So we've got V2 is the longer one and V1 is the shorter one. Now this is all, we're just sort of pushing it all on this plane. So there's some geodesic that is described by these 2 vectors. Now, before we complain too much about it, let me just mention that if this really is, say, a lab for Alice, and this is aligned with her world line, that means her world line is already, say it's free falling, it's already, some sort of geodesic that's tangent to that thing, right? Tangent to E0. So, therefore, the geodesics described by these vectors are going like backwards in time, right? And that's okay. That's okay. You can have geodesics that go backwards in time, and notice that the geodesic defined by this vector right here, which is the basis vector of her tetrad system, that's a space-like curve, right? The lengths along that curve are all positive numbers. Lengths along this curve, using our convention for Minkowski metric, are all going to be negative numbers. And the lengths along this curve are also, well, this is close, right? That's like 45. But say that's like a light cone curve. Maybe that should be 0, right? The length along this curve will be very small numbers. And the point is that geodesics defined by these vectors as the parameter s, right? As this parameter s grows, that you'll propagate along the geodesic backwards in time. As s grows, you move space-like along this geodesic. You don't, very little motion in time, a lot of motion in space. As s grows along this geodesic, you just progress time-like through time. This is a path that a real physical particle could actually take. Mathematically, though, all these geodesics are fine. You can have space-like, you can have time-like geodesics, you can have geodesics where they're parameterized so they go forwards or backwards, right? So keep that in mind. We're every point that's around the lab, right? Any point around the lab. For example, this point here is to the right of the center of the lab. This point is to the left of the center. This point is in the lab's immediate future, right? That's the future point of the lab. This is the point of the lab that was right in its past, the past of the origin of the tetrad. This is a point in the lab that's in the future of the origin of the tetrad and a little to the left, right? So all of these points can be attached to the origin through some geodesic curve that is defined by the initial condition being at the origin and by some vector in the tangent space, which give these 2 initial conditions. Okay, so back to these 2 vectors. The problem with these 2 vectors is they're both pointing in exactly the same direction, and they will both yield a unique geodesic curve in the sense that the curve will, what's going to happen is this is going to be the geodesic curve maybe by V1, right? Now V2 is actually, because it's pointing in the same direction, it's going to give a related curve. And that curve is basically all the same points. But as V1 ticks off values of S along its curve, right? So this curve here is given by the initial conditions V1 and, I'm drawing sideways here, sorry. It's the initial conditions will be V1 and the point A, right? The second curve, the curve given by V2 that has initial conditions V2 and A, it's actually the same curve, but the tick marks, although they both start at 0, right? The tick marks on V2 will be greater, meaning 1 unit of tick along V2 is going to move farther along the curve than 1 unit of tick along V1, right? So the parameterization of the two curves is different, but the actual points that are on the curve are the same. And I got to say, this caused me a lot of confusion for a while until, but I certainly understand it, and so I'm saying this to make it clear to you that all vectors that are pointing in the same direction yield the same curve, but a different parameterization. So that's an important fact, because that's the fact that's going to allow us to sort of create these Riemann normal coordinates. So how do we exploit this? What we do is we go back to the geodesic equation. We're going back to this guy here. And we propose two different curves. First, this guy here is going to represent the geodesic curve that is triggered by the vector v. We'll just assume that it's known that it starts at the point P, right? So when s equals 0, this curve is at the point P, but it's triggered by the vector v. Now, what I don't have in here is the mu's, right? I'm going to drop those for right now, just because we understand that this gives the coordinates, this is 4 different equations that give each of the coordinates for the points along the geodesic. So now I can imagine reparameterizing this curve. I'd reparameterize it by writing it as GV of lambda s. Some factor of the old parameter is going to be the new parameter for the curve. And just by basic, our basic understanding of calculus, right, we know that this is going to be the same curve, but you're going to be stretching out essentially the axis along which the dependent variable axis, and it's going to move faster or slower depending on whether lambda is greater than or less than 1. So that's going to represent a reparameterization of the curve. And then I also want to write down g of lambda v of s, which is basically using sort of this, essentially the same parameter, but the initial vector is going to be multiplied by some factor lambda, and it's going to be the same factor, right? We're going to consider this to be the lambda of this and the lambda of this are going to be the same. So we want to sort of study this and understand what is the difference between this and these two, right? And what we're going to find out is that the difference is not a big deal. So we just proceed as follows. We define a geodesic H with the initial vector v as parameterized by the variable u. We define it as what we would have gotten with g if we made its parameter some factor of u, lambda u, right? So this is being parameterized slightly differently, but we're defining this to be the same curve, right? And what we notice is that if we take the derivative with respect to u of h, we execute the chain rule on g here, we end up with that this tangent vector for the curve h is just lambda times the tangent vector for the curve v. right? And the second derivative of h is just lambda squared times the second derivative of g. And so if we took this and made the substitution into the geodesic equation, we substitute for the second derivative of g and twice for the first derivative of g. This first derivative of g part will give us a lambda squared here, and this will give us a lambda squared out front, and then the g's will, then I can turn all of this into a geodesic equation for h, because the lambda squared pulls out, right? And then I basically get the geodesic equation with HVU in it. So anyway, HVU ends up being a geodesic. So, but it's also a geodesic that starts at the same point, right? And contains all the same points, but its initial vector is its initial tangent vector. The curve h's initial tangent vector is just lambda times the tangent vector of g. So that just means that this guy is actually equal to g of lambda v times u, right? And that's why this is the important relation, right? This is the relation that's the caveat, is if I just start with a different vector, I get the same curve, but I move along it faster or slower by a factor of lambda, right? If lambda is large, then if lambda is large, you're going to, or meaning greater than 1, you're going to move along the curve. It's just going to parameterize the curve faster, but it's the same collection of points. So when we go back to, wait a minute, when we go back to this curve here, what we see is these two vectors, v1 and v2, yield the same collection of points in space-time, but it's all parameterized differently. Okay, so that basically means that every point in space-time has multiple ways of labeling under this system that I proposed earlier, where I would take a point, say this point here, I could label that as v1 some distance s, where s is the blue ticks, or I could label it v2 with some distance s prime, right, where s prime would be the magenta ticks. And so there's two different systems of labeling these points, or two different possible ways of labeling the points. And I have an infinite number of them. For every different collinear vector to v1, I can arbitrarily choose it to set s to be whatever I want, right? I just scale it by lambda in such a way that s is whatever value I wish. And that's the exploit we're gonna do. We're going to set this up so that the point we're interested in, say I call this point B, right? The point B is always going to be, the coordinates of the point B is always going to be along the geodesic curve defined by a parameter distance of 1, right? And some vector v that gives the geodesic parameterized in such a way that the point B has a parameter distance of 1. And I am going to then, I could do this with a point C, right? A point C, I'll call that C. C will have the coordinates of a point along the curve, again, with a parameter distance of 1. I guess I'll call that VB, but a different vector, right? VC. Now, C and B are on the same geodesic, right? But we are going to label the points not by what you would think, which is the distance along the geodesic, the affine parameter along the geodesic to get to the point. Instead, we're going to label the point by the vector that provides a parameterization such that getting to the point, the parameter value is just 1. It's always going to be 1. So the vector is going to change. We're changing the initial conditions
that we use to produce the geodesic equation, in a sense. And those initial conditions are going to actually design in such a way that the different initial conditions are only different in a way that will change the parameterization, but not the actual points along the curve. And that is going to be our trick. And so the coordinate system that I'm interested in is any point B is just described by, well, we know the point B. We know all of them, all the geodesics start at the point P0, right? Which is G mu of 0. And then any vector here, doesn't matter what vector you put here for the initial condition, G mu of 0 will always equal, say, P0. Well, I've been calling it A, right? Hold on, I've been calling it A. So not P0, but A for Alice. So the point B, say the point where Bob is sitting, all I need to know about that point is I need to know the vector that produces the vector that, when combined with the initial point A, produces a geodesic such that the point B is located at an affine parameter distance of s equals 1. And that's going to be true for any point. So that doesn't count as a coordinate. So that vector, this vector is going to be VA, I'll put the hats back on, EA hat, right? And that vector is all I need, because once I have this vector, I know that I can take it, combine it with the center of the lab frame, which I keep wanting to call P, but calling A. I take that, I take the vector who has these components in the basis of the lab frame. I use that to produce a curve, G mu. I go one distance down that curve, right? And then this is V alpha E alpha hat. I go one unit distance down that curve, and those are the coordinates x0, x1, x2, and x3 of the point B, right? And these coordinates, those guys, are called Riemann normal coordinates. I know.
Almost sounds.
And that's what it is. So, to recap, Alice will establish a basis tetrad in her laboratory, and then she will pick a point of interest out there in nearby space-time. And what she will do is she will produce a geodesic that leaves the center of the tetrad and intersects that point. And she will then take that geodesic and find its tangent vector at the center of the lab, and she will tune that tangent vector's length. She'll tune the length of that tangent vector until this point is located at a parameter distance of s equals 1. And then the ultimate choice of the tuned tangent vector. Remember, when I say tuned, what I mean is she's just adjusting its length so that the parameter s equals 1 actually hits the point she's interested in. Then that final tuned tangent vector will have will have components in her tetrad basis, and those components, E alpha, those components will actually be the coordinates of the point, right? So we will use those components to equal the coordinates of the point. That is, and these coordinates are Riemann normal coordinates. Now, there's an alternative way to look at this, which actually I've noticed is more common. This is how it's done in Meissner, Thorne, and Wheeler, which is a book I often cite in these notes. I pointed out it's actually a pretty difficult book. It looks like it's friendly and easy, but it's very comprehensive and it's very insightful, don't get me wrong. But it's not, just because it looks really nice doesn't make it easy. It's actually a pretty challenging book. But it's not as hard as others too, and it's a great book. It's a great book. But this is how they define, how Meissner, Thorne, and Wheeler defines Riemann normal coordinates. The alternative way is actually to do this. The alternative way, which I think I'll probably lean into the alternative way because to me it's a little more intuitive, right? The alternative way has a setup that's very much the same. You create the point, you choose a point out there, and of course this could be any point. It just has to be nearby, right? As I said, it has to be nearby. And and nearby essentially means these geodesics can't start to cross each other, right? Then you have ambiguities in the coordinate system. So it has to be nearby. But instead of tuning this tangent vector, right? Instead of taking the tangent vector and tuning its length to nail down s equals 1, what you do is you take the tangent vector, you scale the tangent vector so it's got unit length. So it's unit length. So I'll call that v hat. How about that? So v hat is normalized, right? It's a normalized tangent vector. So we're selecting the one tangent vector that has normal length. So it's just as long as any of the basis vectors in the system. And now, in this circumstance, S at this point has some value that's, I don't want to say it's arbitrary, but the value of S is determined by the length of the tangent vector that you chose to apply to the geodesic. But now if you force your tangent vector to be unit length, then S is the price you pay is now S is no longer 1. S is just whatever ends up being S. So in this circumstance, what do? How do you define the Riemann normal coordinates? Well, it's sort of, the answer is forced upon us. So V hat still equals V hat alpha hat E alpha hat. Now notice I got all these weird hats, right? This hat is meant to mean unit vector, right? So this is like or normalized vector. I guess unit vector is fair. So that hat means normalized vector. This hat means the tetrad coordinate, right? The tetrad basis. So now I can use, since I'm applying a hat to a Greek letter, this is the tetrad. This is a tetrad index. So this is an example where I slipped into using a Greek subscript, right, alpha, but because I gave it a hat, it's unambiguously the tetrad. Let me clean this up a little bit. Watch. So see what a mess these things can become. So here I wrote alpha hat E alpha hat, and that means this is the tetrad basis. It's also given away by the E. But then because I am used to using hats for unit vectors in elementary physics, right? That hat was there to mean a unit vector. So maybe this hat should be a bar, right? Maybe I should turn this into a bar, right? And then I guess this would be here. I guess I get rid of that V and I make that a V bar, something like that. Either way, this is now set, but S is some value. So what are the coordinates now? Well, there's only one really logical choice. The coordinates of the point B are now going to be B mu equals V0 hat times S, S times V1 hat, S times V2 hat, and S times V3 hat, right? So I'm still taking the components of the unit vector, but now I'm multiplying by what is to amount to the distance along the geodesic line. So S really represents a fine distance along the line, along the geodesic, and that distance now multiplied by these directional cosines, if you like, but multiplied by the unit vector components, and now you still have a four-dimensional locator for B, and these are called Riemann normal coordinates. This is a number, right? These are each in four numbers. These two methods are essentially equivalent, by the way, because if you tune the vector's length to get this to equal 1, well, what does you have? You have a 1 here, a 1 here. Let me just do it in blue. You get a 1, a 1, a 1, and 1, but you've tuned it so that these V's are now absorbing that extra length because this is no longer forced to be normalized. If I force the v's to be normalized, well, then I end up multiplying by s. I think I like the second system better, the second interpretation of the coordinates better, because I really like the idea of everything that's going on at the origin to be normalized. I think that's very convenient. So I'll probably think about it in terms of this. Now, let's take note of something very important here. So let's look at all of the points that are along this geodesic. That point's B. Let me erase the word nearby. Let me extend the geodesic out. And then let me talk about this point here, and this point here, and this point here, and this point here, right? And this will be the points C, D, E, and F. Now that's a geodesic, right? So aside from the awkward fact that this particular geodesic is going off faster than light, which is a problem, maybe I should adjust that so it's a little more plausible. Hold on. No, this is fine, right? A geodesic, these geodesics do not, as I pointed out, have to be time-like at all, right? These are points in space-time, and they have a space-like separation in the language of special relativity. If they're close by, we can do special relativity. They have a space-like separation. That's totally fine. They still deserve coordinates, right? And these are those coordinates, and this is the geodesic that connects them. The point is that, remember, let's go back to our manifold understanding. All of this is actual space-time, right? But space-time is a manifold, so I can map everything in space-time into a coordinate system, right, that is R4. So if I map these points, right, the points I've drawn here, B, C, D, E, and F, if I map in A2, right, A is down here, right, if I map A, B, C, D, E, and F, and I map them into R4 using our manifold mapping, well, this is the coordinate mapping, right? This is the coordinates. Those coordinates are plotted in R4. And A will be here, right? And B will be, say, so this is the, I guess, X0 axis. Well, I don't know. How do I want to do this? This is, well, I guess I got to go with X1 and X0 axis, right? And B is, the way it's going to be V0S, right? And V1S. So this point here, right, is these two coordinates are plotted here, and then these other two are suppressed, right? But then, then that's point B. Point C is going to be, notice how point C is done. Point C, it's the same vector, it's just S is a little farther. So point C is just a different value of S, but these guys are all the same as they were for point B because it's the same geodesic, right? So S changes, and all that means is the components get a little bit bigger, right? Because presumably S is a little bit bigger for C than B. So C is going to actually be right here, right? C, and likewise D is going to be right here, D, and E and F in the coordinates. So you're ending up with the point being, of course, is that this is a perfectly straight line in R4, right? So that's the key. The key is that geodesics in the manifold, right? Geodesic lines in the manifold are actually straight lines in Riemann normal coordinates, right? So geodesics are straight lines in Riemann normal coordinates. And so because of this, right, now if I did consider a freely falling object, right, so I go here to this, I set up E0 and I set up E1 hat and I suppress the other two. Now, in this basis system, if E0 is in fact aligned with the time direction exclusively, so I now shoot out time-like geodesics, I might have a time-like geodesic that looks something like this, right? And this freely falling object, or any freely falling object that's moving along this geodesic in this reference frame, its path in the coordinate system is always going to look like S V alpha hat, right? That's going to be the coordinates along that line. It's going to be a straight line. The point is that objects falling along geodesics in this coordinate system move along straight line paths through the origin. So if I were to literally look at this in terms of R4, everything moving on a geodesic is actually moving on a straight line path. In fact, this is a little bit weird, right, the way I've done this. Hold on. I guess it would be smarter, actually, to look at this picture and then choose a geodesic, a time-like geodesic path would look like this, above 45 degrees, and all objects moving along a time-like geodesic path basically are moving in a straight line in Riemann normal coordinates. And that is the magic that makes everything so important. So I'll write this out because it's so critical, right? Something like this. All geodesic paths are S, V alpha in Riemann normal coordinates, right? With this, these are constants, and this is what's changing, okay? So that is the critical point. And let's just quickly see, before we close this lesson, how this fact makes some very important statements about the geometry of space-time at the location of the laboratory that's using this coordinate system. Now, you will notice this is a little bit weird of a formula, right? I've got this Latin index, or this Greek index up here, and then there's this, well, let's see, what looks like to be a space-time index here, and what looks to be like a tetrad index over here. And that's probably a bit of a problem. This is meant to be just a constant number that we're using, but it is supposed to be matched with this. In other words, I do want the x1 coordinate to equal s times the v1 hat basis vector, right? So I think the way this should actually look is, if I'm going to do it this way, it should look as alpha hat here, and that should be a 1 hat there. So the more I look at this, the more, you want these indices to match up. The problem is you still have to understand this as a coordinate, not as a vector component. So no matter how I match up the indices, I still have the potential confusion. This is a vector component that's constant for this whole process. Anything along this geodesic line it's a constant. In fact, that's another good point, right? This x is actually, to be very clear, it's a geodesic path. So it's x as a function of s, where s is the parameterization of that path. And that parameterization actually equals the most obvious and simple thing, which is just s times a constant. That constant is derived from this unit tangent vector of the geodesic. So although the indices do match, and that is good, this is meant to be a coordinate in Riemann normal coordinates, and this is meant to be a unit vector in the tangent space. So but they're linked together by the geodesic equation, right? That's why you can actually bridge this gap. Okay, so let's have a deeper look at a few of the implications of this. All right, so this little picture is yet another iteration of this, but we choose our unit vector. We identify that unit vector. It's frozen because it's a unit vector, right? We don't tune it, but its parameter length will be tuned for every point along some geodesic. So this represents the geodesic. So now on that geodesic path, anything that is moving along that geodesic path, even hypothetically moving along space-like paths or freely falling along time-like paths, in Riemann normal coordinates, those coordinates are always going to be these straight lines where s is the dependent variable And these are the constants determined that identify the geodesic itself, right? So now let's have a look at the geodesic equation. So here is the geodesic equation. What I've done is I've suppressed the S on the G. The little hat now represents Riemann normal coordinates, right? So this is the Riemann normal coordinates of the geodesic. And here is the geodesic equation in Riemann normal coordinates. Now, in that coordinate system, you're going to have some connection, right? If you have a connection on the overall bird's eye view, right? You have space-time. Space-time has a metric, right? The metric gives us a connection. So there is a connection on the overall bird's eye view. And if there's a connection in one coordinate system, there's a connection in every coordinate system. And we just need to do a transformation from the bird's eye view coordinate system to the Riemann normal coordinate system at this point, and we will determine what these components are. So there is a connection there. Now let's take a look and see if we can learn something about the connection. Well, we do know that this is the form of geodesics. By construction, this is the form of the coordinate system. It's built on these geodesics. All geodesics going through the point in this coordinate system are going to look like this. We've already used the geodesic equation in a sense to make the coordinate system, so it's not a surprise that things should simplify a bit. So what if we substituted this into the geodesic equation? Well, what would we get? Well, the first thing we get is that the derivative of the geodesic is just NA, this constant number, right? Which doesn't look good the way I've drawn it. It's just N alpha hat, and it's just this constant number that is extracted from the initial initial tangent vector of the geodesic itself. So that substitution is going to be very easy for this part of the geodesic equation. But what about this part? Well, that part is going to be 0, right? Because if you take the derivative of this one more time with respect to x, that's a constant, so this goes away. So this goes to 0, and this part here goes to n n beta hat and gamma hat, right? And so therefore we end up with the final expression. This is the final expression. But notice that this has to be true for every geodesic, right? Every geodesic has to have this statement to be true. Not just this particular vector, but that one and that one and that one. It doesn't matter what initial vector we use. It must always be the case that this is 0. And what does that mean? Well, there's only one way that that can be true. And that is in this particular coordinate system, at this particular, which is established only at one point, but without a doubt, in this particular coordinate system, the connection is equal to 0. The connection is equal to 0. And that, boy, does that simplify a lot of stuff. So in this coordinate system, the connection equals 0. And that's because geodesics are straight lines in this coordinate system, and it's a direct consequence of the geodesic equation that the connection for Alice, if she uses this coordinate system, will be 0.
Now, critically, the connection is 0 at Alice's point. Remember, we still have a full-sized, fulsome space-time here. At this point, the connection's not 0, because that point doesn't have, that's not the place where these geodesics all go through and emanate from. It's only right here, because remember the connection, alpha, beta, gamma, I guess in this case, the connection is a function of the coordinates, right? X mu, right? The connection is a function of the coordinates, right? So it's only when this equals Alice's position does this equal 0. You've made it 0 at the one place in the space-time where this coordinate system has its origin. The location of the tetrad's origin, that's where the connection is zero. If you could make the connection zero on the entire space-time, then the space-time would be it would be of absolutely no interest. I mean, remember the metric is what determines this connection, right? So the metric's changing everywhere, the connection changes everywhere. But we found a coordinate system that forces the connection will change everywhere, but it's got it so that right here at least it's zero. We'll talk a little bit more about that when we redevelop this entire subject from the ground up using the Einstein Equivalence principle. This is very related, by the way, to our initial derivation of the geodesic equation. In one of the earliest lectures, we derived the geodesic equation using the Einstein equivalence principle. We're basically going to repeat that and establish this tetrad. That's what we're going to do in our next lecture. But this turns out not to be the only thing of interest. So all the tensors, the metric tensor, the curvature tensor, all of these things can be described in a different way at this point, exploiting this fact. And we're going to have to go through all of that in order to ultimately get to our goal, which is to come up with a good interpretation of the scalar curvature tensor. Okay, so in our next lecture, we're going to redo this work, but from the ground up. And instead of talking about emanating geodesics, we're going to talk about the Einstein equivalence principle and some other things. But we're going to but Riemann normal coordinates are worth another additional lecture. Okay, so we'll see you next time.